Hello, sorry. Hello everyone, and a very good morning. It's 10:33, and today I am currently making a video about Taylor series and McLaren series, and I found a very interesting question because this question, the way I solve it is not just plug in the formula that we've known for Taylor series, but is to identify the pattern and create our general series for all n, which is zero. And in this video, I'm not like an experienced math math student who solves Taylor series daily. But this video is all about those who are beginning on learning this without even using the formula and finding the pattern while doing the question. Well, I'll be showing on how I obtain the general form, the series, or to be more specific, Taylor series. Now, this question wants us to find the Taylor series generated by f of x, 1 divided by 1 minus x to the power of 3 at x is equal to 0. Now, this is the same as a Maclaurin series because we know the Maclaurin series of f is the Taylor series generated by f at x is equal to 0. And here we are. So, now the first things first is we will try, hold on, first, we have to list out the first n terms, which is generated by the Taylor series. Okay, we will list it out and we will find a pattern from there and see what is our general form. Okay, remember today's video is not all about plugging in the formula, but is to find the pattern and try to create a series from there. And maybe who knows, maybe you're an expert. The more you do, the more you're familiar with the patterns and you have no trouble on finding it in a short amount of time. Okay, so first things first, we have to find the nth derivative, or you don't need to find the nth derivative, but just find the first nth derivative, maybe up until sixth derivative or even seventh. But in this case, I only found up until the third derivative because from there I could easily see the pattern. Okay, so the zero or the derivative zeroth derivative is f of x basically. So the first derivative, we know that if you want to use the power rule, which you convert this reciprocal function to a, you bring up the numerator using the laws of indices, then you could, it depends on your taste of applying which rule. Okay, so I'll be using this notation to just indicating that this is the first derivative and so on. So the first derivative for this function is 3 over 1 minus x to the power of 4. And then the second derivative would be 12 over 1 minus x to the power 5. And then the other one will be f3, x is equal to 60 over 1 minus x to the power 6. Alright, so far so good. Now, what we are about to do is just by knowing that the Taylor series is a sum of polynomials, and by using the formula for the Taylor series, which is sum it, f of a plus f first derivative of a, x divided by 1 factorial. You know the formula. But now we want to generate a general formula. But this is just the first n terms we are listing out, which is what I'm talking about is this one, f of k, a, x minus a power of k over k factorial. And this is, we would like to find the sum for the first k terms, right? But I'll be listing out to see where to see the pattern for it, that we could okay, now we can build something. So I believe there's an easier way for those who are used to solving Taylor series. Let me just put it here. Okay, and all right, let's list it out. So first we have to find the sum of the first n terms. So f of 0 So basically it's x power 0, but x to power 0 is 1, so we don't need to write that down, and divided by 0 factorial, which implies 1 as well, so we just leave it as it is, which is 0 as well, because we want to find at center 0, or at x is equal to 0. And the next one will be f1, 0, x minus, well, minus 0. X minus 0 implies 0, so you are left with x to the power of 1, and divided by 1 factorial. Okay, so far so good. 2 up of 0, x to the power 2. Now we start here by writing down the factorial. Or if you want to write it for the first two terms here, well, just to see the pattern itself, so there's no problem with that one. And then the third one will be so. Well, obviously this goes to infinity. That doesn't end. It's an infinite series. We are trying to generate infinite series that represents the function. So okay, okay. Now just plug in the values that you've put here into your functions and your derivatives. So it will be, we are starting with, I believe it will be 1 plus with 3x over, well, 3x over 1 factorial plus with 12x squared over 2 factorial plus 60x cubed over 3 factorial plus dot 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 dot. Okay, so this is pretty easy if you can see that each term, well, I'm not saying it's easy, I'm saying this part here, this one with the x term and the factorials are easy to create a pattern, because we know that when n is equal to 0, then x power 0, x power 1, x power 2, and so on. This implies as well for the denominator, which is 0 factorial, 1 factorial. But how about the coefficients here? How do we build a pattern which is suitable? 1 is a coefficient of x power 0. So let's try and see the pattern. So it will be 1, okay, for when n is 0. 1 times 3, okay, for the first, for n is equal to 1. 1 times 3 times 4 for when n is equal to 2. 1 times 3 times 4 times 5 for n is equal to 3. Now, it looks like a factorial without the multiple of 2. Because we know that, let's say we have 4 factorial, which implies that it is a multiple of 1 times 2 times 3 times 4. But in this case, like this one here, there is no multiple of 2. It doesn't multiply with 2. And that is the same as each term. So, well, it looks like it divides by 2, right? Okay. So it means that, well, this is also equivalent to 1 times 2 times 3 divided by 2. 1 times 2 times 3 times 4 divided by 2. And this is as well 1 times 2 times 3 times 4 times 5 divided by 2. And so on. So, oh yeah, this is well 1 over 2. So this is when n is equal to 0, n is equal to 1, n is equal to 2, and n is equal to 3, and so on. So what does that mean? It means that, let's say here, will be, well, 1 factorial over 2. This will be 3 factorial over 2. This will be 1 factorial, 2 fact, yeah, 4 factorial over 2, 5 factorial over 2. Okay, so we can see there's a pattern. Okay, so far so good. We are making progress now. Okay, so now we have to find the general term for it. Okay, so we know this, right? 1 factorial is equivalent to when, it's also equivalent to 0 factorial over 2. Sorry, 1 and 0, n times 2 minus 1. 0 factorial, hold up, n minus 1, n plus 3, and okay, sorry, this is the same as, sorry, It's not 1 divided by 2. It's 2 factorial over 2. That's correct. My apologies. In other words, 1 times 2 over 2, 2 factorial over 2. Okay, so this creates a pattern, a really nice pattern to say the least. Okay, so how do we do it? Now that's the question. How are we supposed to go from here? All right, n plus 2. All right. Well, we could argue that this could be simplified as 0 plus 2 factorial over 2. Oh, my apologies. Give me a second. Okay, 0 plus 2 factorial over 2. And this will be 1 plus 2. Sorry, my bracket's a bit big. 1 plus 2 factorial over 2. Oops. Yeah, okay. And then here will be 1. Sorry, not 1. 2 plus 2 factorial over 2. This will be 2 plus 3 factorial over 2. So the values in front here corresponds to each n value. Sorry, this is not the right order. I would like to show this pattern. Okay, and so on. So what does this mean? This means that the general formula will be n plus 2 factorial over 2. Huh. So remember, this is for the coefficients. So now, okay, we have obtained our pattern here, our general formula for the coefficients. And how are we supposed to express this as a series, infinite series? Okay, now this is for the coefficients, and now for x. For x, we know it begins with, well, 1 is equivalent to x plus 0. Well, 1 divided by 1 factorial, 1 factorial. We know that 3, sorry, x over, it's not 1, sorry, it's 0. 1 factorial, which means that this is x power of 1 over, well, 1 factorial. And then the next will be 1 over, yeah, I love that one, x squared over 2 factorial, okay, for when n is equal to 2. And then, well, x power 3 over 3 factorial, and so on. So this implies the general formula for x would be x to the power of n over n factorial. So now we have obtained for the variable x and for our coefficients. Okay, now we have to combine them and express that as a series, an infinite series. So, well, it's a multiple for one another. This is a multiple of this. Therefore, we could combine them and express it as the n is equal to 0. We begin with 0, as you can see here. For both of them, we begin with 0. Add up until infinity, n plus 2 factorial, okay, over 2, x power of n over n factorial. Well, that's very nice. And now we could simplify further, because n plus 2 factorial is equivalent to n plus 2, n plus 1, n factorial divided by 2 times with x power of n over n factorial. Okay, and well, we can simplify from here, and we are left with this n plus 2, n plus 1 divided by 2, x power of n. So that's our Taylor series when x is equal to 0 for the function. So it's very nice. But I'll not be talking about convergence or divergence. I'm just basically trying to show the expression for Taylor series here. And yeah, this is how we obtain the pattern. Yep, so far everything seems nice and in place. Okay, so there you go. This is your Taylor series. So the conclusion is that knowing the pattern is very important, and through more exercises you could see the patterns very clearly. here, but here is one of them. And I apologize if my my working isn't that efficient, but this video is more to those who want to find a pattern. I believe those who are already expert in this field should have no problem, but this is for those who want to see how it expressed. Okay, and yeah, I believe that's about it. Thank you very much, and all the best.